Oh. Right. Down the line.
Okay, hi. We'll just wait for 2 minutes in case someone else is joining.
Yes, that's fine.
Okay, maybe we can start and then people can join as it goes on. So I will just share my screen.
Okay.
Okay, so yeah, welcome to the session, problem solving session. So for everyone who's watching and who's in the meeting. So my name is Zenia. These sessions, by now you know, halfway through the course already, that these are for solving problems related to the assignment and for recapping the week's lectures so that your understanding of the course is enhanced. As always, all the course materials are recorded and also put on my website. The slides are also shared. I hope you have been able to access it. And this is my mail ID, and you can contact me in case of anything you want to clarify or any topic you want me to cover in the lectures in detail. You can do that. Okay. So we are talking about the week 7 lectures now. By now we have got a good handle on the different kinds of particles and force carriers that exist in the standard model, along with some basic quantum field theory that is enabling us to write what could be the Lagrangians that describe the particles and the various interactions between them. You've also seen that the way that we describe things in particle physics is using group theory. The mathematical language of the standard model or the grammar of the standard model is very much based on group theory. Different kinds of groups can be mapped onto different kinds of interactions, and similarly, different kinds of particles, whether they be fermions, bosons, etc., they may obey certain symmetries, which are then mapped onto again different kinds of groups and their interactions. So it becomes important for us to understand that when we are assigning this mathematical concept to a particle or its interaction, we are also indirectly saying something about its nature. And this is what we are trying to do when we write mathematical theories in physics, right? We try to describe things in mathematical language so that we get a better idea of how certain parameters depend on each other instead of just writing in English words. So in particle physics, as you've seen, the best way to do that is in the language of group theory. And we have already seen some examples of how group theory helps us. So now we are moving on to the parts of the standard model that give it, its elusive or, interesting nature, which is mainly about gauge fields, gauge invariance, and the concept of symmetry breaking. Symmetry breaking is again a very interesting concept. If you recall, the very first lecture of this course was about, or one of the very first week of this course were taught about Noether's theorem, which is about mathematical physics theorem about symmetries, and symmetries play a very central role in physics and particularly in the construction of the standard model. So it becomes important to know that what happens when symmetry is broken and what are the physical consequences of this, and also to learn about something called the Higgs field, which I'm sure everyone knows because it was such a important and celebrated discovery in 2012 when the proof of the Higgs field was actually confirmed. Even though it was suggested in the 1970s, it was only confirmed in 2012 by the detection of something called the Higgs boson, which is basically the quanta of the Higgs field. So this is the idea behind the Higgs field. So we'll try to quickly go through all the symmetry breaking, its consequences in terms of the Goldstone theorems and Goldstone bosons, and as well as look at the consequence of all this, which is the Higgs field, and how it gives the different particle species in the standard model, how it assigns a mass to them. Okay, so as you know, we have spent the last few weeks talking about how there are different kinds of particles, and the particles behavior and degrees of freedom and other things depend on what kind of yeah, anyway, what kind of spin it has, and that uh, on its own gives you an idea of what kind of equation of motion it follows. So different particles can have different kinds of interactions, and this is codified by the Lagrangians that they have. So each of them have a Lagrangian. Once you have Lagrangian, although here I should say it is a Lagrangian density, because we are talking about fields, we are not just talking about point particles. So different particles of different spins have different Lagrangians. And from once you have a Lagrangian, you know that you can apply this Euler-Lagrange mechanism. And from that, you can get what could be the equation of motion for these things. So this is how you think about the different parts of the standard model. So now we are going to talk about a very interesting idea, which is about spontaneous symmetry breaking. So this week you saw this concept, but let's try to understand it again from a few simple examples. So this today I have prepared my notes from two books, which I have been using for the last several weeks as well. One is Symmetry and the Standard Model by Matthew Robinson, and the other is Quantum Field Theory for the Gifted Amateur. I think in fourth chapter of Matthew Robinson's book, and chapter 46 or 47 of Quantum Field Theory for the Gifted Amateur. So if you have those books, you can go and look at them. They'll give you a more complete picture, but I'll try to explain it to you anyway. So to illustrate the concept of symmetry breaking, let's first look at a Lagrangian. Okay, so this is a simple complex scalar field Lagrangian. You can see that there is some sort of kinetic term and a mass term. And you can always write the mass term in terms of some potential, right? So this has a U1 symmetry. U1 basically, is a group theory term, but you can think of U1 as corresponding to just a phase, right? So this has symmetry in the sense that if I add an arbitrary phase e power I alpha to phi, then all these the Lagrangian is not changed, the equations remain the same. So that's why I say that it has a U1 symmetry. Okay, you can also see that you can graph a V. So the first graph corresponds to this Lagrangian. You can see that you can plot V as a function of phi, and you can also already see that it is symmetric about this minimum point, which is 0, right? So the vacuum of the theory ends up to be 0, and the vacuum corresponds to the complete absence of any particle. So when phi is equal to 0, obviously the whole Lagrangian becomes 0. So there is no particle at that point, and depending on the other parts, there are things. But it's not necessary that our potential has to have this form, right? We can have a mass term, but we can also have some additional terms. So now if you just consider a quartic term in the potential, so quartic means I'm going to add a phi to the power 4 term. Okay, phi is some real constant, and notice that the Lagrangian still has a global phi symmetry. So this phi is some constant. So again, if I just change phi, I'm saying small phi, if I change a small phi to something like phi times e power I alpha, then I still get the same thing. So if I plug this back, you can see that phi dagger is going to give me an e power minus I alpha, and phi is giving me e power I alpha. So in both the terms, the e power I alpha phase terms cancel out. So the symmetry is still there, but when we graph V versus phi, you get something different. So now you can see that the minimum is not at a single point, but so this is a kind of like a 2D, so supposed to be kind of like there are two axes. So it's a 3D picture, which is not very well seen. But basically, there's a whole ring of points. The phi is equal to 0 points. It becomes the minimum becomes this whole ring of points, right? This entire circle is the minimum. So from this, you know
Yes.
that there is, yeah,
No,
from
didn't ask me question.
Yeah. So basically, phi is equal to capital phi represents the minimum of the theory. But instead of being just a single point like in the simple potential, because of this extra term, we see that that is shifted up, and actually the minima becomes this whole circle. Okay. So this is called a degeneracy of vacua. Okay. There are infinite number of vacuums because you can consider any point on that circle is going to be vacuum, and there is a degeneracy of vacuum. Okay. But obviously, in a real example, if you want to take a degenerate vacuum, then you can say that there is a degenerate vacuum. So the degenerate vacuum is said to be parameterized by e power I alpha, because we can just, which is a global U1. And there will be a vacuum for every value of alpha located as phi is equal to capital phi. So if we want to actually make this a physical theory, we have to choose a vacuum by hand, which means that I am breaking that symmetry. So once I say that, okay, this point is the vacuum, then immediately the potential is not symmetric about the vacuum. Whereas in this theory, it was very much symmetric about the vacuum. So this is what it means by spontaneous symmetry breaking, which basically symmetry breaking is kind of understood, which is that you have, you know, a symmetry which was originally there in the theory, which later is not there. The spontaneous part is because naturally, because of energy minimization, your system will tend to choose a single point. And you can see that because of the concept that we have degenerate vacua or we have infinite vacua, because of that concept, the moment I choose a point, the moment the system chooses a minimum energy state, immediately the symmetry is broken. So this is not like only a particle physics thing, right? Suppose I have a pencil. If you can see my video, I don't know if it's visible, but suppose I have a pencil, right? So if I have a pencil and I balance it on the table, then in principle the pencil can fall in any direction, right? It can fall in any of the 2 pi circle directions which are around me. But when I leave it, it's eventually going to fall in one direction. So if you actually write the potential for this pencil's motion, it will be depending on gravity, right? It will depend on gravity. If you ignore air resistance and all other forces, it's just going to depend on gravity. And gravity doesn't tell you that pencil should only fall in this direction or that direction. Gravity tells that in a particular plane, it can fall in any direction. So it's a similar situation to this spontaneous symmetry, to this quartic potential that we have. But eventually, if I leave the pencil, the system is going to choose one direction. It fell down here, right? Whereas it could have fallen here, it could have fallen here, it could have fallen here. So by leaving the pencil, it has chosen a minimum. Okay. By choosing the minimum, the system has broken the symmetry that was originally there. So basically, there were some initial conditions on the pencil. Those initial conditions led to the pencil choosing a particular minimum, which then broke the symmetry of the system. Okay, so this is a very simple example, but similar things happen in the fields that we study. Not every field has this nice behavior where the minimum is at one point. There are theories that we write for the particles, as you'll see, where the minimum actually comes out to be in a whole circle of things, and that makes it susceptible, or um, um, that makes it have this tendency, or by evolution itself, by energy minimization, the system will choose one vacuum out of the degenerate vacua, and that will break the symmetry of the system. So this is what is the concept of spontaneous symmetry breaking. So so this is basically tells us that we have to choose a vacuum by hand. And as you can see from this theory, the how does the pencil choose which vacuum to go to, right? That is not there in our Lagrangian. Remember that Lagrangian is not a unique thing, right? Any physical system can be described by multiple Lagrangians. In the same way, multiple physical systems can also be described by the same Lagrangian. Your Lagrangian doesn't account for the initial conditions. There may be some very small air resistance or something or the other which we have not accounted for in a Lagrangian that makes the pencil to fall in this way. So the point is that it's really the initial conditions which break the symmetry. But once the energy minimization based on the initial conditions is done, then we cannot have that symmetry anymore. That symmetry is spontaneously broken. So basically you can see that for spontaneous symmetry breaking, I really need two things. One is that I really need a degenerate vacuum of solutions for my potential, because I need multiple vacuum that's possible, such that when the initial conditions are put, the pencil, or the system automatically will collapse into one particular state. So this is the idea. Okay. So the basically the idea is that once I've chosen the thing, the system is no longer symmetric. It doesn't obey this U1 symmetry. You can't just add e power I alpha. It doesn't obey that symmetry anymore, because phi has some particular value. You cannot shift it arbitrarily. Okay. So this is the idea behind spontaneous symmetry breaking. But why do we care about this? Because we care about this because spontaneous symmetry breaking has some very interesting consequences. So let's see what they are. So this is understood if we now, now we have changed our coordinate. Now we are no longer like this. We are, we are in this point where the theory has collapsed to this point. So if it is collapsed to this point, then we have to rewrite the theory in terms of a new vacuum. Right. So this is a change of basis. We are changing from one coordinate system to another coordinate system, fixing the minimum to be whatever point the potential has chosen. So we expand around the constant vacuum value phi with the new field. So instead of phi, we are going to what is the new field, which is the around this minimum, which is alpha plus I beta. Because it's a complex field, let's just write it as explicitly as alpha plus I beta. And then therefore, phi dagger, which is a complex conjugate, will just be phi plus, again, phi is a real value, some real field value. So it will be, or it's a constant value. You don't have to worry about it. This is alpha minus I beta. Okay, phi is real, so don't worry about it. Now we can write out the Lagrangian. So the Lagrangian is del mu phi. This is the Lagrangian, right? Del mu phi star, del mu phi minus V. And in V, you have two terms. One is phi dagger phi and one is capital phi square, which is a real number. So instead of phi dagger and phi, we are going to substitute alpha plus I beta and alpha minus, I mean, capital phi plus alpha plus I beta and capital phi plus alpha minus I beta. So you can see that when you write this down, this is the terms, and then you can group the terms together. So now you can see something interesting, right? We are left with, first of all, we are left with many terms, right? And it's not, the character of the Lagrangian has changed. How has the Lagrangian changed? Well, first of all, now I have two fields. I have a field alpha and I have a field beta also. And you can see that alpha, it has a kinetic term and a mass term, right? It looks similar to this, except that the mass is not just m, it's something like 4 lambda m squared, phi squared. But fine, if I just call this by some other name like capital M, then you know that this is a mass term. But basically, I have kinetic term, mass term. Whereas the field beta only has a kinetic term. There is no beta squared term, and that tells me that beta is a massless particle. So already the theory of one complex scalar field has become into one massive real field and one massless real field. Right? The complex scalar field has broken down into a massive real field, real scalar field alpha, and a massless real scalar field beta. And then there are a bunch of interactions. So this is alpha interacting with itself at a 3 vertex. This is alpha beta squared. This is alpha 4. So 4 alphas are interacting, alpha square, beta 4. So there are all these different kinds of self interaction and interaction between the two real fields. But the main point is this part, which is that now instead of a complex scalar field where real and
Sorry.
imaginary, hello,
No, nothing. Sorry.
yeah, where they have a real and imaginary complex field where both of the parts were, together, we now have broken it down into two real fields where one has a mass and the other does not have a mass. Okay, so it turns out that whenever you break a symmetry, this kind of turn is inevitable. And this is a theorem in mathematics and physics, and it's called that the vanishing of the mass is a manifestation of something called Goldstone's theorem, which says that breaking a continuous symmetry always results in a massless excitation known as a Goldstone mode. The massless particle associated with this excitation is known as a Goldstone boson. So whenever you break a continuous symmetry, you get an associated massless mode with it. Okay. How many such massless modes are there is something that we can count when we go to more complex examples. But this is the simplest example of a Goldstone boson, where we just have U1 symmetry, which is with respect to a phase. Just by destroying that phase symmetry, we got a massless real field from the complex scalar field. We have now broken it down to a massive real field and a massless real field. Okay, so this theory has no obvious U1 symmetry. For this reason, writing this field in terms of fluctuations around the vacuum we choose is called breaking the symmetry. The symmetry is still there, but it can't be seen in this form. So remember that by breaking the symmetry, the mathematical potential is the same, right? We have made a coordinate transformation. So the symmetry is still there. It's just not very manifest here. The symmetry structure has gone into creating this massive and massless parts. And what happens is when we break global symmetries as we have done, it always results in a massless boson. And these particles are called Goldstone bosons. So this is Goldstone boson, and this is the simplest example where I had a global symmetry. By global symmetry, I mean that it's just, e power I alpha, where alpha is a constant. It applies to all the points equally. And that symmetry, when I broke, I automatically got a, massless boson as Goldstone's theorem predicts.
The
Now
alpha
the
and beta, I have a question. The alpha and beta are infinitesimal or are they regular variables?
So alpha and beta are two real fields. So instead of now we had initially had this complex scalar field. Now
Yes.
because we have done a coordinate transformation, we are just this
Yes.
still we are writing it as alpha and beta. Alpha and beta are two real fields.
But they say that we're expanding around the constant vacuum value of phi. So is there any way that alpha and beta are actually very small in magnitude or something like that?
Uh, yeah, no, okay, yeah, maybe that's true, but I don't think this is not like a Taylor expansion. We are just doing a
Yes, yes.
coordinate transformation. We are not doing a Taylor expansion. There is no
Okay.
like higher powers of alpha and beta. Instead of writing it everything in terms of phi, we are writing in terms of alpha and beta. But basically, we are shifting the origin. Initially, the origin was here. Now we are shifting the origin to whatever is the minimum. So in the
Yes, yes.
new coordinate, the coordinates are alpha and beta. So it's not
Mm.
Taylor expansion, it's a shifting of coordinates.
Okay.
Okay.
Thank you.
So yeah, sure. So this is the point, right? So whenever you have, so there are two things we saw. One, which is that when you have degenerate vacua in a potential, that means there are infinite or multiple vacuum that the theory can collapse into. Once it collapses into that theory and the symmetry is broken, then we actually see that when we coordinate transform, or when we observe things from that new system, then we end up with an extra degree of freedom. That extra degree of freedom is basically your one, or not even an extra degree of freedom, that's wrong. One of the degrees of freedom becomes a massless boson. That's what you get up. Okay, so you always have this associated vanishing of the mass, which is what is a Goldstone's theorem. Okay, so now this example was kind of simple, or it is the simplest version of symmetry breaking because it was based on a global symmetry, right? Where the same symmetry applied everywhere in space, and it was just a constant offset in terms of a phase. But what if we have a local symmetry? And by what I mean by a local symmetry is where the symmetry itself is dependent on space time. So instead of having e power I alpha, where alpha is a constant, suppose I change it to alpha of x, which means that the value of alpha depends on x, right? So it then something interesting happens, which is that if you want this kind of symmetry to be obeyed by your system, you necessarily need to introduce something called a gauge field. Okay, so this is similar to how if you want to write a theory that obeys Lorentz covariance or Lorentz invariance, right? We know that we have to mix up space and time, so we can't just use ordinary vectors. We have to use a new mathematical concept, which is four vectors. Similarly, when you deal with local symmetries, where the symmetry itself is dependent on the coordinate in space and time, you have to use something called a gauge field in order to completely describe that symmetry. So first, let's understand why we need this gauge field in the first place. So, just to recap, the first example of spontaneous symmetry breaking we saw is a global symmetry where it was something like we are adding e power I alpha to every, we are multiplying by e power I alpha. The system is invariant and that alpha was a constant. Now we are asking the question, if I change alpha instead of being a constant to a variable which is depending on where you are in space, then you can see that the field transforms a field by different amount at every point in space time. So, can a theory, first of all, the question is, can a theory be invariant in these conditions? The answer is yes, it can. And the way to make such a continuous symmetry, continuous local symmetry work is by introducing the concept of gauge fields. And we have already kind of seen gauge fields, right? The vector potential in electromagnetism is a gauge field, where there is a local symmetry there, and in terms of the charge, and we have introduced the gauge field. But let's try to keep it general. Let's not restrict to electromagnetism. Let's take a general transformation where psi x is the same as psi x under some local transformation. Okay, so the problem is that in this case, when I multiply by e power I alpha, this term doesn't change, and this term also doesn't change because e power I alpha is a constant, so derivative doesn't act on it, right? But when I have a local symmetry like this, the derivative does act on it, which means I will be end up with a bunch of extra terms. Okay. And when I have a bunch of extra terms, I can't really call the symmetry the same anymore. I can't really call the theory the same anymore. So this is why this concept of gauge field is important, because it helps us to cancel off the extra terms. So you'll see exactly what I'm talking about in this example. So yeah, the good news is that the mass term m squared psi dagger psi, what we called phi, we are calling psi here, doesn't matter. Some complex field doesn't change when we transform locally, because here I'll have a e power I alpha, here I'll have a e power minus I alpha. So nothing is going to change. The bad news is that the term involving the derivatives does. The kinetic term changes because now alpha is also a function of x, so the derivative also acts on it. So you can see that um, if I do just del mu of psi of x, then I actually have to, use the chain rule. I have to differentiate this keeping this constant and this keeping that constant. So I end up with something like this, right? End up with some structure like this. And similarly, if you act it on the complex conjugate, you get something else. So the first term in the Lagrangian actually becomes this whole thing, right? So then you might say that how is this a symmetry? Because it's completely different. The Lagrangian has completely changed. So how can I call it a symmetry? So that's where this concept of gauge field is going to help us, which is that all these extra terms can be absorbed if we redefine the derivative. So now, as along with redefining the field, we also have to redefine the derivative. Again, I'm telling you, it's simply like Lorentz transformations, where the rules of relativity tell us that first of all the transformations are different, but also the things the transformation acts on are different, right? We have to use four vectors. We can't just use normal vectors. Similarly, when we do when there is a local continuous symmetry, because it's depending on the space time, the derivative itself changes, and this is what is something called a covariant derivative. So what you'll see is, having alpha depend on x has robbed the theory of its U1 symmetry. It's not invariant with respect to local U1 transformations. But let's see if we can restore this local symmetry. To do this, we add a new field A mu, which basically cancels out the terms. Okay. And what will happen is we introduce A mu into the derivative by redefining the derivative like this. So this is example what we do in electromagnetism, right? In classical field theory also, in classical Lagrangian mechanics also, if you've taken Lagrangian mechanics and you are asked to write the Lagrangian of a electromagnetic field, then you end up writing something like this, right? The momentum operator looks like this. So basically, this is what is called the covariant derivative. So I know Q, A, other things make us think of electromagnetism, but this is not unique to electromagnetism. If you have a symmetry, then it's a local symmetry, which means it depends on space time, then it's going to mess up your derivatives. So in order to bring back the derivatives in the correct form, we have to also take care of the change to this derivative, because the space time itself we are messing with in the symmetry, right?
I have a
So this,
question.
yeah, yeah, sure.
So actually, I was reading relativity, general relativity, and
Yes,
the covariant derivative appears there because of, as a result of the curvature of space-time, right?
yes.
So does that breaking of the symmetry or the messing with the symmetry curves up space-time in some way? Is there something like that?
Yeah, that's a good question. So those okay. So right now we don't have a way to combine particle physics and GR, but yeah, covariant derivative also plays a role in GR, as you very correctly said, because of the curvature of space time. Because again,
Yes,
the normal derivative is not correct because space time is
yes.
curved, and we are thinking that it's a straight line, so d by dx cannot do. We have to add some terms. I don't
Mm.
know if it's a symmetry. We can interpret it as a symmetry breaking there. It's a different concept, but the idea is the same here. Basically, the symmetry also messes with what we are calling the space time. Their curvature messes with space time. But
Mm.
yeah, I don't know how to combine this. That's why people have not been able to combine particle physics and GRE.
Yes, yes. Okay.
Yeah.
Thank you.
But yeah, it's the same concept. One way the curvature of space time is messing around with your space, what you call space time. Here it's like, because we have local symmetry, we have to take care of that in the space time. That's what we are just imposing that on the space time. Okay, good. So now you have this new object, which is called the covariant derivative. And if we do the transformation such that we take psi to psi e power ia, at the same time, we also fix d mu, which is the derivative to the covariant derivative. If we do both of these transformations together, saying that the field transforms like this, then basically, if you say the field transforms like this, that fixes the covariant derivative. And by doing both these transformations together, you can keep the local U1 symmetry that you wanted. Okay. So here Q is called the coupling strength and A mu is like the gauge field. So remember that whenever you have a local symmetry, you'll automatically end up with what is called a gauge field. Okay. Because of this derivative business. So you can see that if psi x, so here in this example, they are actually showing you that it's true, because if psi x goes to e power I alpha, then del mu gives you this extra terms as we saw. But then if we fix it as d mu, you can see that all the extra terms get absorbed into d mu, and we are end up with the same thing. So d mu on psi is the same as d mu on psi e power I alpha. So that means that in order to write the Lagrangian as an invariant or a symmetric one, instead of writing everything in del mu, we should write in d mu. Similar to how in GR, if we want to write an actual tensor theory, we have to write everything in terms of covariant derivative. So the same concept here.
Yes.
Okay. Fine. So that tells us that if our theory should be invariant, we do two transformations together. And the theory which has a field introduced to produce invariance in respect to local transformations is known as a gauge theory. And this field is known as a gauge field. Okay. So then AMU can give its own field strength to the Lagrangian, as we know from, for example, Maxwell's Lagrangian. You know that we add this half f mu nu term, like that. The gauge field can have its own kinetic term in the Lagrangian, and that can help us to again get the correct equations of motion. So already we have seen a gauge theory, which is electromagnetism. You can see that electromagnetism provides an example of such a theory. It's a theory described in terms of a vector field, which is used to form the Lagrangian, and from the equations of motion follow. Okay, so why is this all important? Because let's go back to symmetry breaking. So in the first part of today, I showed you what happens when we break a global symmetry. Here, the symmetry was constant throughout space-time. It didn't depend on the space-time. So that's why I didn't have to have any extra gauge fields in my Lagrangian. Now, what if I do the same procedure where I end up with a ring of vacuum and I choose one minima and that breaks the symmetry? What if I do that, but at the same time, um, I have a local symmetry with a gauge field? Then what happens? So then what happens is quite interesting. And this leads us exactly into the Higgs mechanism. So in the previous section, we broke a U1 symmetry global. In this section, we'll break a local U1 and see what happens. So we begin with the Lagrangian. So you can see that now we are writing a local symmetry. So you can see that already we have replaced the del mu with the capital D mu. So instead of writing capital, if we just, because we have a local symmetry, you know that we already have to replace all my del mu, small del mu with capital D mu. That's what is replaced here. We have the usual mass or potential term, Along with that, we have an extra kinetic term because this gauge field can have its own action, own contribution to the Lagrangian, which is what is this term. Okay, so similar to how in electromagnetism, the A mu part has, its own term through the F mu nu tensor. Similarly, whenever we have added a gauge field, we have to then add its contribution to Lagrangian separately also. Okay, so external source J mu is equal to 0. Let's again assume that V has a quartic form, which I showed you, so that we have this ring of solutions again. Okay, so that vacuum has a U1 degeneracy as psi is equal to capital psi. So because our U1 is now local, we can choose the gauge alpha of x so that not only is the vacuum real, but also so that psi is always real. Okay, so we are going to choose a particular psi such that we keep psi to be real without any loss of generality. Let's just try what happens. So let's write psi to be phi plus h. Now we have chosen in such a way that instead of alpha plus I beta, because we can choose which point in space time is all having different points. So let's choose such a point that my vacuum ends up being a real vacuum, okay, instead of a complex vacuum. So now again, I'm doing the same coordinate transformation. Okay, before I was doing from phi to alpha plus I beta. Here I want to transform into a real vacuum only. Before I didn't have that freedom because the symmetry was constant everywhere. So I can't say that symmetry is real here, the vacuum is real here, vacuum is not real here. Here, because the symmetry, the vacuum may change with every point because the symmetry is also different and local at every point. I can just choose a point which I call real. Okay. So now I'm doing the coordinate transformation from phi, I'm doing to h. Okay. Sorry that psi and phi are mixed because I'm taking from two different books, but basically phi and psi are interchangeable. But yeah, phi, this is the vacuum plus some field h, which is my now coordinate transformation. Instead of having origin at 0, I'm going to have origin at phi, capital phi. So now if I do the same thing, which is that instead of having phi here, I'm going to have capital phi and expand. You can see that I have this term. I have my f mu mu, which is seems to be not affected. And then of course, phi, all the phi terms are replaced, right? But now another interesting thing happens, which is that if I now expand this, I end up with, here you can see that I end up with some massive term f mu nu and some interaction term, right? This q square phi square a square. So this a is from the gauge field, phi is the vacuum, and etc. So the where the allowed interaction term includes a vertex connecting an h and two a's. So I think, yeah, this is L interactions. So they've not written it down. So before breaking, we had a complex scalar field and a massless vector field a mu with two polarization states because it's a photon. So here in this book, they have specifically taken the electromagnetic gauge field. That's why A mu is the electromagnetic vector potential, F mu nu is the electromagnetic tensor. But remember, the things I'm saying are general. Okay, electromagnetism obeys a U1 symmetry, so it's the simplest example we can do for this. So before the symmetry breaking, we had this complex scalar field phi and massless vector field A mu with two polarization states because we know it's a photon. Now we have a single real scalar h with some mass and also a with a mass. So you can see that now there are two mass terms. So remember, whenever you have a field squared with some constants in front of it, if you have something like some constant c times field square, that's a mass term. So for example, in this field, this is the kinetic term because it has derivatives and such, and this is the mass term. Similarly here, this is the kinetic term because actually F mu nu, if you remember the definition of F mu nu, it comes from del mu A nu and so on. So this is the kinetic term for a gauge field and this is the mass term. So now the initially massless A, because you remember in the original theory, I didn't write any mass term for A. Now it has actually a mass term as well. In other words, our force carrying particle AMU has gained mass. We started with a theory with no mass, and by merely breaking the symmetry, we have introduced mass into our theory. This mechanism for introducing mass into the theory is called the Higgs mechanism. So basically, when you have a local symmetry, So we saw two things, right? One was when we had a global symmetry, and if we are in a situation where we have degenerate vacuum, then it's going, the theory is going to, the energy minimization is going to choose one vacuum, and that's going to result in the formation of some massless mode, which is called a Goldstone boson. But if we start with a local continuous symmetry, then first of all, we can't just write the Lagrangian as it is. We have to introduce covariant derivative. In order to introduce a covariant derivative, we also need to introduce this gauge field. And what happens is when you break this continuous local symmetry, the gauge field, which initially did not have mass, ends up gaining mass. So this was a Higgs mechanism, which was first discovered by Peter Higgs. And the excitation of the Higgs field, which is what we call is called a Higgs boson, where the consequence of global symmetry breaking is a massless boson called the Goldstone boson. The consequence of a local symmetry breaking is that the gauge field, which came about as a result of the symmetry being local, acquires mass. So this is very important. We didn't have a gauge field in the first example. The reason was because that theory was not local. It was a global theory, and as such, I did not need to worry about the derivative being different or something like that, right? Whereas here, because it's a global local theory, it depends on the space-time itself, which means that we have to be careful about how we take our derivatives. And for that, we needed to introduce this new mathematical concept, which is a gauge field. And when we break the symmetry, we find that it's a gauge field which gains mass. Okay, so this is a very important concept. So you can already see how symmetry breaking can have very interesting physical consequences for theories. Okay, so this is the idea. Okay, so now let's try to apply this concept. So now we have seen this concept in two ways. One was global U1, where the symmetry was a constant, and the other was a local U1, where the symmetry itself was depending on space-time, right? Now let's try to apply this concept to what should be our universe, right? Initially, our universe would have the way that we understand the universe and the particle content right now is that we are in currently a symmetry broken universe. Initially, we would have started with some state of high symmetry, and that was broken to give the universe we are in now. Why do we think this? So there are a lot of things. One is that when people were first writing the theory of the weak interaction, so you already saw that in the very first lecture, first week's lecture itself, you saw that weak interaction has this parity violation, right? Where left-handed particles obey weak interaction differently than right-handed particles. And then if you put in CP also, you see that CP violation is also there to some extent in the weak sector. It's expected in the strong sector, not so much seen. But the main thing is parity violation is seen. And when people are writing Lagrangian for the weak interaction, the one which leads to beta decay and all that, when they try to fit the data into, when they try to, write down terms which fit the experimental data, what they found is that the theory which fit the data was that the weak interaction only acts on left-handed chirality particles. Okay. Um, so helicity and chirality are the same for massless particles, but for massive particles is a little different. You know that for massless particles, always the chirality and the handedness are the same. But in massive particles, because helicity tells me about how the spin and momentum are aligned, because massive particles can have frame transformations, and the momentum sign can change between them, the helicity can also change. So the intrinsic property of the particle is the chirality. Okay. For massless particles, because they always go at the speed of light, both of them are the same. But massive particles, because the momentum can change sign, they may be different. Okay. So let's only talk about chirality, because that is the one which is invariant in all frames. Okay. I just want to mention that. The point is that at some point while writing this weak interaction Lagrangian, people found out that in order to keep the theory consistent with what was seen from data from experiments, you require a theory, the weak interaction or the weak force to act only on the left-handed or the left chiral particles. So this means, okay, because we saw the Dirac equation last time, so the weak interaction only acts on left-handed fermions. Okay, we saw the Dirac equation last time, how to write equations for fermions. And you saw that in the Dirac equation, the mass term mixes the left and right-handed particles, right? So maybe I can just show you. Maybe I don't know if it was okay. I think it was last week. I don't remember. Dirac equations. So yeah. So remember that if you have the Dirac equation, where is it? So you can see that if the mass is zero, then the right-handed and left-handed equations are independent of each other. But if the mass of the fermion is there, I'm talking about spin half particles because all the neutrons, protons, quarks, electrons, quarks, sorry, not neutrons, protons, electrons, neutrino, quark are all spin half. So yeah, so we can use the Dirac equation to describe them. So point is that if this mass is zero, then right-handed equation is independent of left-handed equation. On the other hand, if they have some mass, some small mass, then right and left are mixed together. But we already know that the weak interaction, as I said, from experiments and other things, when you're trying to write a theory consistent with experiments, we saw that the weak interaction only seems to act on left-handed particles. This was indicated to us by parity violation experiment of Madame Wu and other things, right? So that means that in the beginning, the theory cannot have any mass terms, right? Because mass term will require to mix left and right. But then I can't write if I want to write a general theory, a gauge invariant theory, I can't write a theory that only acts on left-handed particles when it also has right-handed terms. So because of this, in the early universe, it's believed that the masses of all the particles were zero. Then what happened was, like how we saw now, some continuous symmetry was there within the particles. Okay, we'll see what continuous symmetry it was. That was broken because again the universe, chose it collapsed into a finite vacuum. You'll see exactly how all this process, but we've seen a simple case now. Once the universe chose a vacuum state, then that symmetry is broken. We see that when the symmetry is broken, all the gauge fields gain mass, right? So this is how the particles gained mass, the gauge bosons also gained mass. Okay. So we'll see the full extent of this next week when we talk about electroweak symmetry breaking. But right now, just understand that the Higgs mechanism, which I'm talking about, it is a general mechanism. It is not to particularly do with electroweak symmetry breaking, although that was where it was applied. But this Higgs mechanism, as you saw, I just took some random field, I added a U1 local symmetry to it, and if I do this whole calculation, I automatically end up with a mu having mass. So a similar kind of thing happened in our universe. So we already know why the symmetry was there in our universe because of all what I said, which is that we know that in the initial part, the left-handed and right-handed particles behave differently. So left-handed particles obey their own symmetry, right-handed particles obey their own symmetry. Then somehow, and we couldn't write mass terms because they'll combine them. And then somehow eventually the symmetry got broken, leading to mass and leading to the mixing of the left and right-handed terms. So we cannot just write a mass term to mix the left and right-handed terms. We need to write it in terms of an extra field, and this extra field is what is called the Higgs field. Okay, so let's look at that whole process once from top to bottom. So before symmetry breaking, let's imagine the universe a moment after the Big Bang. It's more symmetrical than the universe in which we live. Specifically, the lepton fields have an internal SU2 cross U1 symmetry. So this U1 is something like electromagnetism and SU2 is something like weak field. Okay. The reason I am not calling it exactly electromagnetism and weak force is because the electromagnetism and weak force we have right now is after this symmetry breaking happened. So before this, it was SU2 cross U1. After it breaks, we'll only be left with U1. Okay. So you will see how that happens now.
Basically,
So
we only know some of the symmetries of the fields that were there.
yeah, exactly. So we know that because the weak field acted on left-handed particles, there was a SU2 symmetry that was obeyed by all the left-handed particles, and we write that as SU2 doublets. And we know that overall U1 you can add to any particle, like a phase you can add, and it was there. And the symmetry in the early universe was combined. It was SU2 cross U1. Okay, because there was no mass to mix anything, so we were able to have this. In our current universe, because mass is there, this SU2 symmetry is spoiled. Okay, we don't have only the weak force only acting on, we actually do have left and right fields talking to each other in terms of mass terms. So we have to go from SU2 cross U1 to U1. So there's a symmetry breaking because SU2 symmetry was broken. So that's what we'll see what happens.
Okay.
So in around a very small time, the universe cools below some temperature and undergoes a symmetry breaking phase transition. So again, energy minimization means that one vacuum will be chosen, and this leads to electroweak symmetry breaking, which is what is described by the Weinberg-Salam model. Again, the details of electroweak symmetry breaking is in, I think, week 8 lectures. Right now, let's understand it broadly, and then the details of like the W boson, Z boson, how they come about, and the photon, how we get the exact fields we see now, we'll see in the next lecture. Okay. So before symmetry breaking, neutrinos and electrons are both massless particles. Electrons are possible in both left and right-handed forms, but neutrinos only existed in left-handed form. This we already know. As I explained in one of the very early lectures, neutrinos are like vampires. They don't have a reflection in the current standard model. They are only left-handed, and they are considered to be massless in the standard model, even though we know that from experiments, neutrinos have some small mass. But as far as standard model is concerned, neutrinos are massless, chargeless, left-handed particle. Neutrino and electron are fermions and are therefore excitation in Fermi fields. We know that their Lagrangian will be the Dirac-Lagrangian because we know these are spin-half particles. So we'll have to write a Dirac-Lagrangian for each of them. So we can write for the electron. So here it's written as E, but this is, this E is both the electron, muon, tau. It can stand for any of the three generations. Okay. So let's just deal with one generation at a time. And you'll see later how the different generations can mix among themselves. By generation, I mean electron and electron neutrinos one generation, muon and muon neutrinos another generation, tau and tau neutrino another generation. Okay, so you can think of this E as standing for either the electron, muon, or tau. The same term will be there. This L basically stands for the electron, left-handed electron. ER stands for the right-handed electron. So you can see that there are three terms. This del dash is their notation for a covariant derivative. Okay, so don't worry about this. So this is just without any mass terms we are going to have. We are thinking of the early universe where there was symmetry was still preserved. So the weak interaction acted on the left-handed particles, U1 was there, and all together we had a symmetry. So this you saw in your notes also. So this is just from your notes. You can see that we can write different, basically different symmetries as we have kept seeing. The way we write everything in particle physics is in terms of these groups, right? Groups correspond to different symmetries. So the SU2 weak force corresponds to, and with every symmetry, you have the associated generators, which are kind of like the gauge fields. And that generators are, generators which give you how to construct the gauge fields and the field strength tensors and all that. So we saw a little bit about this. I spoke about generators and how to find them in my last week lectures. The structure constants, all of these things are related. So this SU2 weak is the symmetry enjoyed by the weak sector. But remember that this only applies to the left-handed particles. This U1 is Y. Y is hypercharged. So because we are in the early universe, it's not electric charge because we have not yet broken the symmetry to get to our current universe. We are still in the early universe where the thing was different. So that time the charge is denoted by Y, just to distinguish it from Q, which is our current charge. Okay, so don't get confused. This is kind of the same. It couples to a U1 kind of thing. Our current electromagnetic charge is also described by U1, but it's a different coupling because it's after symmetry breaking. So you can see that
So the
similarly.
symmetry breaking, as you had said, symmetry breaking adds a massive boson, right? Gives them
Yes, yes,
the Higgs boson. But you said there is hypercharge before the symmetry breaking, then there is charge now. The
yes.
charge also is there a way that charge can change or some? Is there a way
Yeah,
the charge
yeah.
can change?
So what happens is when the symmetry is broken, as you will see, I think in the electroweak symmetry breaking, when you see the full thing, you'll see it more explicitly. But this SU2 cross U1, not all, it's not completely broken. So SU2 cross U1 gets broken and only U1 remains. That U1, what is remaining is what we interpret as electromagnetism. So that U1 corresponds to current electromagnetism, which we see. So all the charges of electron fermions, which we see, are corresponding to that U1. But before
Okay.
the symmetry breaking, that U1 is different. So just to distinguish between this U1 and that U1, we call this hypercharge and we call this charge. They are,
Okay.
that's why. So you can see that, yeah. So I think Nirmal has combined these left-handed terms into one doublet, SU2 doublet, because that's where SU2 acts on, and then the right-handed particle is its own thing. So that's this notation. I think it's there in the lecture notes, and here quarks are also there. So these are the left-handed quarks, these are the right-handed quarks, then these are the left-handed leptons, and these are the right-handed leptons. So you can see that the left-handed particles are in doublets because they obey SU2. Okay, and here you can see that this is the charge under the color force. This is the charge under the weak force, and this is the charge under U1 Y, which is a hypercharge. Okay, and each of them, as you can see, can correspond to any number of generators. So you know, you whatever you see here, it's multiplied by 3 because you have 3 generation of leptons, and you also have 3 generation of quarks. Okay. So, yeah, so the point is that weak interaction maximally violates parity. It only acts on left-handed spins. This we know from experiments. Okay, I'm not going into the details of that, but basically, yeah, this is just about the Feynman diagrams. The point is that when we write the covariant derivatives or the kinetic terms, it comes out like this. So this is just these are the generators and the structure constants and basically the gauge fields and the various generators together put together so that we can write the kinetic term. So there'll be one kinetic term for the color field, one for the weak field, and one for this photon field. Okay, but we cannot write a mass term because, as I said, the mass term will combine left and right, and right now there is a very specific symmetry for left. There is no such symmetry for the right. So if we write the term together, it breaks the symmetry, so we cannot explicitly write it. But we know from our experience that electrons have mass. Neutrino doesn't have mass, but quarks have masses, even though if they are small. So how do we bring that mass about in our theory? For that only this Higgs mechanism was brought in. Okay, so again, this is just an explanation of why there are no mass terms. Basically, there can't be mass terms because of gauge invariance. So I've put the slides here, you can check it. But this is about mass, why fermions we can't write mass term for the fermion. We cannot write it for gauge bosons also because they are not invariant under gauge transformation, basically. So that is the idea. So any gauge boson must be massless. Similarly, so if you want to write the mass term, you do need to bring in an extra scalar particle. In the standard model is a Higgs, and if it has a non-zero web or a vacuum expectation value, which means like how we saw the symmetry breaking, then the symmetry will appear to be broken, and that gives gauge bosons their masses. So this is the exact mechanism that we saw for the local U1, right, where we ended up with this massive H field. Similarly, we are going to end up with when we break the SU2 symmetry also, we are going to end up with some massive particles. So yeah, this is just an explanation of all that. If the Higgs is a doublet, then we can also have a product of left and right-handed thing, and this gets interpreted as a mass term. So basically, the point is that if we have an extra field, right, apart from these quark fermion fields and the gauge bosons, which are the force mediators. So right now we have the fermion fields, which are the quarks, leptons, etc. We have the gauge fields, which are basically your force terms, right? The force carriers, the photons, gluons, and so on. And yeah, right now they are not photon. It's in the early universe, so it's some hypercharged B mu, not A mu. But along with this, we have to add an extra field. We have to add the Higgs field. Only if you add the Higgs field, then this mathematics works out. So this was found in the 1970s by Peter Higgs, and some similar work was seen in superconductivity, where also this spontaneous symmetry breaking is seen. The point is that this mathematics was worked out, and it was known that, okay, if whenever you have a field, you will have an excitation of that field. And so the way to confirm this was to observe the excitation of the Higgs field, which is the Higgs boson. Okay, so the point is that every other part of the theory is all like mixed up together, right? The Higgs field is mixed up with the electroweak fields and symmetry breaking and all that. But this all works out mathematically. It seems to be mathematically consistent theory. But how can we actually experimentally verify that this is happening? If we have an extra field, we should see an extra particle. So that was why people were looking for Higgs boson, because if we can see the Higgs boson, or we can see a particle that looks like Higgs boson, because people predicted its properties, we see a particle that looks like the Higgs boson, that automatically tells us there's an extra field in the system, and that is what is causing, and therefore everything, if there's an extra field, then mathematically and physically we can work out a theory. So that's why the discovery of Higgs boson was very important, and it had to be confirmed. So even though theory was written in 1970s, it took until 2012 when people had enough significant detection level, because so many particles are produced. In order to really be sure that this is the particle, we have to really observe it, many events, and make sure, to do some statistical analysis to see that this is actually the particle or not. So this is the idea behind the Higgs field. The Higgs field is just a way for us to write mass terms without
I have a question
violating.
here.
Yeah, yeah.
You said Gauss bosons don't have mass, right?
Yes,
So, I mean, the only massless particle that we have encountered so far is the photon. I mean,
exactly. So
before particle physics, and the photon doesn't have rest mass, right?
yes, exactly. So that's a
It, but
very good.
okay,
Yeah,
but
yeah. Continue.
it has. I mean, so it has to have the speed c to make up for the rest mass becoming zero, right?
Yes.
So are these other Gauss bosons also moving the speed of light?
So that's a very good question. So the point is that the initial phase, right? In the early universe, all the gauge bosons were massless. Okay, that's why we are calling them by some different name like B mu nu and W mu nu. Then, when the symmetry breaking happens, as you saw in this case also, when we had simple symmetry, if it's a local symmetry, we break it. Even the gauge boson gets a mass. And that's why the other force carriers like W boson, Z boson, which are the weak field force carriers, they do have a mass. They are around 100 GeV. Okay, and this was actually how the electroweak symmetry breaking theory was predicted, because people predicted that if symmetry breaking happens, then there will be these force carrier particles which are around 100 GeV. And after this
Okay.
theory was made, immediately these particles were detected. So we knew that, okay, they come from this symmetry breaking mechanism. So then the
Okay.
question becomes, why doesn't the photon have mass? Because if symmetry breaking is going to give gauge bosons mass, then photon cannot be massless. So it turns out when symmetry breaking happens, you'll see the exact theory. I don't have this in this lecture. I don't have. I think it's in next week. I'll discuss this. When the electroweak, exactly if you write the electroweak symmetry breaking, then you'll see that there are 3 degrees of freedom, or 3 bosons which gain mass, and there's one combination of bosons which remains massless. So the 3 bosons that gain mass are W plus, W minus, and Z boson, and the one that remains massless is the photon. So basically, this W mu mu and B mu mu, they're all massless in the beginning. But then because of symmetry breaking, 3 of them gain mass and one remains massless. So we'll see why exactly 3 gain mass and one remains massless when you look at his electroweak symmetry breaking in detail. So the field which we see now is after the symmetry breaking. So that's why some of them have mass and some don't. So photon
Okay.
is massless, but
Okay.
others have mass. Yes. Okay, so this is about mass term. So as I said, if you can't write mass term in early universe, because it will lead to gauge invariance, which will violate gauge invariance. From what we see from experiments, weak field only acts on left-handed particle. So in order to have mass term properly, we need this extra field. When we add this extra field, you will see that this extra field is what undergoes the symmetry breaking and leads to the broken symmetry and all that. Okay, so so we are going to write the components in this form of this column vector. And yeah, so this is just about the similar thing to what we did previously, which is that there's a local U1 symmetry, e to the power I beta x. We know that if we have a local symmetry, if we want the theory to be invariant around it, we have to introduce a gauge field. And here Y is the hypercharge of the theory, similar to how in electromagnetism, when you write the covariant derivative, you have this Q. Q is the electric charge. Similarly, here, because we don't want to call it electromagnetism, this is before symmetry breaking. So we are calling it by different name. Okay, that's what it's called, hypercharge. And similarly, you also have this other symmetry, which is SU2. Okay, and this SU2 comes from, as I said, the weak interaction. So it acts only on the left-handed particles. So you can see that the left-handed particles get affected in some way, but the right-handed particles don't. Okay, the right-handed particle remains the same. It doesn't pick up any extra term. So this is called the weak isospin. Okay, again, this is before symmetry breaking. We call these names. That is the weak isospin and the hypercharge. So for this, we need a gauge transformation, which is WU, and it transforms according to this. Why does it have this structure? It has this structure because SU2 is a non-abelian group. So it's the way it transforms under non-abelian gauge transformations are different. You can go check the previous lecture for details about this. Basically, it's because structure constants become non-zero. Okay, so you can see that we may turn the internal dial labeled U1 weak hypercharge without changing the properties of the state of the early universe. The dial serves to multiply the fields by position dependent phase factors whose effects are cancelled by the gauge field B mu. Similarly, SU2 may be turned up, or basically you can imagine as changing the properties without any physical consequence. The dial mixes up the massless fields, neutrino and left-handed electron, multiplies them by position dependent phases, but its effects are cancelled by the gauge field W mu of X. The transformation has no effect on the right-handed sector. Okay, so here it's only written for leptons, but quarks also have the same thing. Okay, so now you have seen local U1 and SU2 for our field components. Together they make this theory locally invariant with SU2 cross U1. In order to make these symmetries of the Lagrangian, we now need to replace derivatives with covariant derivatives. This also we know. If we have a local symmetry, we cannot write derivatives. We have to write covariant derivatives. So now del mu of mu and del mu of mu is coming by here. And you can see that we are going to write the left-handed and right-handed components separately, where left-handed component will have both the neutrino and electron, whereas right-handed component will only have the electron, because this is not affected. We just are separating it because this is not affected by SU2. So it won't have this extra term that is corresponding to SU2. So basically now the left-handed covariant derivative looks like this because it has contribution from SU2 transformation and from the U1 transformation. The right-handed covariant derivative looks like this, only has transformation from the U1. Okay. So our resulting locally symmetric. So finally, if you write all the terms of the Lagrangian in terms of this, by introducing the covariant derivative, by introducing the gauge field, and by whenever you introduce gauge field, remember you have to write the kinetic term of the gauge field. If you do all three of these, then this is the Lagrangian you're left with. So remember, these are just Dirac terms, right? This is a Dirac term, this is a Dirac term, and then these are the field kinetic terms. Okay, remember we still don't have masses in the theory, that's why I don't have any mass terms. So you can see that the right-handed particles have one covariant derivative, the left-handed particle has one covariant derivative, because left-handed particle has both SU2 and U1, right-handed particle only has U1. And these are the different field strength tensors in SU2 and U1. Again, why this is having this form is because of field theory stuff. You can go check about representation theory in the last week's lectures. Okay. So now is the interesting part where to make all this work in terms of the masses, we are going to introduce a massive complex scalar field called the Higgs field into the universe. So as I said, right now we have no way to mix left and right without violating the symmetry. So we have to introduce an extra field. Instead of introducing a mass term, we are going to introduce an extra field, which is what we call the Higgs field. It's the interaction of this field with left and right-handed electron, which will make the electrons massive particles. Because there's no right-handed neutrino, similar Higgs mechanism cannot happen on the neutrino. Okay. The Higgs field has four components which are conveniently arranged into a two-component vector. So, yeah, without any loss of generality, you can write the Higgs field to be like this. Okay, it's basically a Higgs doublet, it's called. And yeah, basically this is the magnitude. Basically people assign some hypercharge and weak isospin to it such that you will see the mass transformations and all work out. So it turns out that it has to have hypercharge of this much, weak isospin of this much, then it transforms like this. Okay. And the point is that if we want to know how Higgs field transforms under U1 and SU2, then because it has y is equal to +1 and weak isospin, you can define the transformations. And again, whenever I have a local symmetry like SU2 or U1, I have to immediately change the derivative. I have to change the derivative to covariant derivative. So then this new field is going to have this covariant derivative del mu of phi, which is having SU2 and U1. So it is both charged under SU2 and U1. It then gives a contribution L phi to the Lagrangian. So this is just the Higgs contribution to the Lagrangian. So here you can see that the Higgs field has this term, some mass term and some potential term as well. Okay. So the positive mass term gives rise to this kind of potential. This is called a Mexican hat potential. And what's interesting about this potential is that it has very much the similar form to the very first potential I showed you in the beginning, right? This kind of potential. Okay, not
Yes.
exactly, but yeah. So that means that it also has the same problem, or not problem, it's actually good for us. It also has the same property, which is that all its minima lie on a circle, right? So eventually, when the field chooses a vacuum, there's going to be symmetry breaking. It's going to give mass to the bosons. So this is how the W and Z bosons and the fermions get mass, because because the fermions get mass because the Higgs field is able to write out these mass terms that mix up left and right. And you know that in a Dirac Lagrangian, when I have terms that combine both left and right, that's a mass term. On the other hand, the gauge bosons get mass because I know that when symmetry breaking happens, then automatically my gauge fields will get mass. So the full idea of this we'll see when we see electroweak symmetry breaking in detail. I think that's in next week, but this is the basic idea of the Higgs field. And so this, you can see the positive mass term gives rise to the potential shown here, from which we will see that the Higgs field is unstable to symmetry breaking. For an ordinary scalar field with negative mass term, it will be phi 0. But with this Mexican hat potential, the ground state is not phi is equal to 0, implying that ground state of a universe containing the broken symmetry Higgs field will be permeated by a uniform field phi of 0. And this field's quantum is what we call the Higgs boson. So remember from quantum field theory, little bit of basics which I taught you. Every field can lead to its own quanta, which are the particles we observe. The quanta of the Higgs field is a Higgs boson, and that is what was observed in CERN. So the Higgs field is different. It's this doublet of, various complex scalar fields. It arises to this excitation called the Higgs boson. And observing the Higgs boson only confirm the Higgs field, because every other part of the theory is kind of caught up with, electromagnetism or weak field. So we can't really isolate the effect of the Higgs field from any of them. Only the Higgs boson is the independent measure of this theory. And by observing the Higgs boson, we understood that there is an extra particle, that extra field which is arising to this particle, which gives rise to this particle, which we had not accounted for till now. And that was exactly what was predicted by the theory.
Is
Okay,
there any way
so
to study the Higgs field just as it is? I mean, it's a field theory, right? So we can write the
yes, yes.
Lagrangian and
Exactly. So this is the Lagrangian of the Higgs field. As you see that we also have,
okay,
there'll
yes.
be interactions of the Higgs field with the electron and right-handed electron and left-handed electron and so on, because that's how because the Higgs field has to finally communicate with our scalar fields. So the thing was, people had already written the theory of Higgs field before it was before the Higgs boson was observed. Okay, so
Okay.
mathematically everything was consistent. People actually wrote the theory first. Then they said that, okay, if this theory is fully correct, then there should be one extra particle in the standard model, which is the Higgs boson. So by observing the Higgs boson, we came to know that all the theory of Higgs field from
That's correct.
1970s is correct. That's why Peter Higgs got the Nobel Prize immediately when the Higgs boson was discovered, because he had actually predicted, and others had predicted this phenomena, but it was only experimentally confirmed once the particle was observed.
Yes. Yes.
Okay. So, right. So, along with the Higgs field's own terms in the Lagrangian, we also have to write some terms that couple the Higgs field to the left and right-handed fields, right? Otherwise, it doesn't make sense. So, this is why the Higgs field can lead to mass-like terms, because whenever you combine the left and right-handed parts of a Dirac spinner, that's a mass term. That's what's called a mass term. So that's how you get the Lagrangian. So you can see that now we have the Dirac terms, we have the covariant derivative of the Higgs field and its terms. Then we have interaction of the left-handed fields, the Higgs field and the right-handed fields. This is basically what gives mass to the electron. Then you have the field strength tensor. To all together, this is the field theory of electroweak symmetry, of the electroweak theory. And once this theory symmetry breaks, is how we get the WZ bosons and the photon that we see today. So next week we'll talk about how exactly this was experimentally verified. It was done by Weinberg, Stephen Weinberg, and Abdus Salam, and they got the Nobel Prize for this because they predicted exactly what the mass of the gauge bosons will be after the symmetry breaking, and exactly those masses were observed at particle accelerators. Okay, so this is what you saw in the lecture notes also. So you can see that the potential kind of looks like this. So you end up with something like a mass term. And because there's no unique vacuum, there's a degenerate vacuum. So eventually you end up with the true vacuum, which is the vacuum expectation value, breaking the symmetry. And by picking one thing, a point at random, you end up with spontaneous symmetry breaking, which, as I said, is determined by initial conditions. So this is SU2 cross U1, and that is collapsed to just U1. Okay. So the ground state breaks the SU2 cross U1, and from this broken symmetry, you end up with again, the notation might be slightly different between different things, but basically you end up with one of the components having having some value, the other components go to zero. You can find it by gauge transformations, similar to how we eliminated the other polarizations of the photon. We'll do the same thing here. So here you can see that huh. So basically, when we break a non-abelian symmetry, our choice of vacuum may be invariant. It may still have some residual symmetry, so the symmetry is not completely broken. And what you find is that the vacuum is still invariant with respect to some combination, some phase which is a combination of the hypercharge and the Wiki isospin. And this combination is what we call the new charge, the electric charge, which we observe today. Because remember, we are living in this universe after symmetry breaking. So that is why we distinguished between hypercharge and electromagnetic charge, because you can see that Y is not equal to Q. Y by 2 plus isospin somehow, and then the Pauli matrices all together is what is giving Q, right? So this E power IQ, this symmetry is what leads to Maxwell's electromagnetism. So initially electromagnetism, weak field were all jumbled together. Then the Higgs field underwent symmetry breaking, which broke the symmetries, SU2 symmetry of the theory, because the Higgs field coupled left and right. So now there's no SU2 symmetry, but you're still left back with a residual U1. This residual U1 is what we interpret as electromagnetism, and its gauge boson is the photon. So again, next week I'll probably, because this is already going long, next week I'll go through the electroweak process in detail, and we'll see how after symmetry breaking, the gauge fields combine in such a way that there are three terms which have mass terms and one term which is left massless. Similar to our very first example, which I started with today, right? In this global symmetry breaking, you are left behind with one field which had some mass term with it, and then one field which was massless. So in electroweak symmetry breaking, it turns out that there will be three terms like this, not exactly looking like this. The parameters will be different, and one term which only has a kinetic term. That will be the photon, the other will be the W and Z bosons. So this is the insight that got the Nobel Prize. So I'll just go. Okay, I'll wind up now, maybe in 10 minutes, so that we can discuss questions. But yeah, let's just finish off this. Yeah. So basically, you can do gauge transformations and reduce the Higgs field to this kind of form. This is how people write it. And by the spontaneous symmetry breaking, you can predict the existence of massive electrons, massless neutrinos, massless photons, and massive Z, W and Z particles. As I said, this we'll discuss in detail next week. Okay, so this was also shown in the lecture. So I think Nirmal used slightly different notation. So like G and W, V plus H here in the book I was using it, they use 5-1, 5-2, 5-3. But basically just, you can see that at the vacuum point, if you expand the terms and you combine them, you can see that three of the terms just go to zero. You're left behind with only this term. And this is again because of Goldstone theorem, because Goldstone theorem tells us that for every generator of the symmetry broken, there is always one Goldstone mode. So here from SU2, we go to U1. So SU2 has three generators. Three generators are now broken. So we are left behind with three massless bosons, and that one massive boson we are left with is a massive sort of excitation we get is the Higgs boson. Okay, so remember, local symmetries when they are broken, they end up with massless modes of excitation, which are different. But they are also left. They also give mass to the gauge boson, gauge fields, right? So, in some sense, people say that the gauge bosons eat the massless modes. That's what they say. Like the W and Z bosons eat up this G1, G2, G3, and they gain the mass. That's like a terminology that some people use. Okay, so yeah, basically this whole mechanism is what leads to electroweak symmetry breaking. Remember, in the beginning, electromagnetism and weak force were combined together in SU2 cross U1. After symmetry breaking, you're left with only U1, and that leads to W and Z boson getting mass and the photon being massless. So we'll see exactly about this next week. I've put some videos here. Maybe I'll not play them because we are at 7:20. I want to solve the problems, so you can watch them in your own time. This is a nice set because it tells you about how the Higgs was actually discovered. Short 2-minute videos that tell you about how the Higgs was discovered and what led to it. There's a small animated videos that you can watch in your own time if you're interested. Okay. Okay, before we end, one last thing I want to touch on is there was another example of symmetry, spontaneous symmetry breaking you saw. But instead of the electroweak sector, this was in the quark sector, right? The color sector, which is basically something called chiral symmetry breaking. This also leads to the prediction of some massive particles, and you'll see how. So, chiral symmetry breaking is basically, as it says, that there is a chiral symmetry, there is an approximate chiral symmetry. Chiral means left or right, because the quarks are so nearly massless, and quarks are also fermions of spin half. They can be written by the Dirac Lagrangian. Because they're so nearly massless, you can write them as almost as massless particles. And you just saw that when Dirac particles are massless, they have independent left and right handed equations, which leads to a chiral symmetry between them, right? So what was found is that, basically, because QCD Lagrangian have quark masses which are very small when compared to the QCD scale, they're only like 5 to 10 MeV. So to a good approximation, we can neglect the quark masses. Let's just consider only the up and down quarks, which have very small masses, and those are the quarks which are composed which lead to the protons and neutrons anyway. So to do good approximation, we can neglect the quark masses in the QCD Lagrangian. So the QCD Lagrangian has an SU2 cross SU2 chiral symmetry. It's written as U2 because U2 is U1 cross SU2, but here the U1 doesn't matter, only SU2 matters. Okay, so there is an SU2 left symmetry and there's an SU2 right symmetry separately, and overall also there's a symmetry. So this is what is called chiral symmetry. Now, again, what happens is this symmetry also gets broken because as the universe cools down, this there are these like Cooper pair kind of quark condensates that form that are like Q bar Q. Okay, quark anti-quark pairs combined together. They are not mesons; they are just condensates like a Cooper pair. And when this happens, again, because Q bar Q breaks the symmetry between SU2 and SU2, that basically, yeah. So initially, this is a Lagrangian. You can see that left-handed term, right-handed term, left-handed term, right-handed term, SU2L, SU2R symmetry. As time cools down, they basically combine because they are this Q bar Q condensates, and this is just left behind with one SU2. Okay, so already you know that when I break the symmetry, how many ever generators correspond to the broken symmetry, that many Goldstone modes I'll be left with. For example, here, because SU2 cross U1 led to U1, that means SU2 was eliminated. SU2 has three generators. Those three generators are realized as three Goldstone bosons. Similarly, here we started off with two SU2s. We end up with only one SU2 corresponding to isospin being conserved. This that means that one SU2 was broken in the whole process. That means three generators will be left behind, which means that we should get three massless particles. But remember that this is not a perfect symmetry, right? This was an approximate symmetry because in reality the quark masses are there. They are not zero. They are still having some small mass. So this is also an approximate symmetry breaking. So that's why we end up with pions. Pions, actually, you can do this calculation and predict the mass of the pions by putting back the mass terms after this and predicting. So that's why there are three pions which correspond to the three Goldstone bosons, except they are kind of not called Goldstone bosons. They are called pseudo Goldstone bosons because they have some small mass. So basically, mu and md is not zero. So chiral symmetry is approximate. So that's why the pions are formed, and they are basically quark condensates formed from this. So again, this is still okay because the pion mass is very small when compared to something like the neutron and the proton. So because everything we are dealing with are have masses which are much smaller than the scales of the problem, we can the same kind of mathematical treatment happens, except the pions do gain some small mass, right?
I
They
have a
gain
question.
heavy mass. Yeah.
Uh, I mean, what we have done so far is very exact calculations, right? There is no
Yes.
approximations, nothing.
Yeah. Yeah, yeah.
So then what brings in this pseudo Goldstone boson? They look like some sort of a result of some approximate calculation because of which some
Yeah, yeah.
masses got in there.
So I agree. I agree. So this is, for example, if you do a similar kind of calculation to get any other meson's mass, like kaon's mass, you won't get a very good value. So this is an approximation. The point is that in this specific case, it's a good approximation because the U and D quark masses are very small. They are very much smaller than everything else. So
Okay, there
it
is
ends up
approximate.
kind of giving us a sensible answer, but we cannot. You're right, because this is, it's still an approximate symmetry, so we won't exactly get. That's why they are not zero mass as Goldstone
Okay,
predicts. They are so.
what is approximate? Which is the approximate symmetry?
So the approximate symmetry here is that the masses of the quarks are very small, so it's almost like they are massless. So because of that, we have a chiral symmetry where you have Su2L and Su2R conserved separately. Okay, in reality,
Okay,
there is some small mass term, but it's so
so there will
small.
be
It's all,
coupling.
yeah, there will be coupling, but that
Mm,
mass term, the M is orders of magnitude smaller than everything else. So
mm,
it's almost like it doesn't exist. That's why we get pion masses are predicted okay. But if we go for kaon, because kaon also has strange quark, and strange quark has a mass. It has 100 MeV mass, which is not too small. So the terms are important. So if you try to do this similar funda to get the kaon mass, you will not get a good answer. So here in this case, because the U and D quarks are very small masses, it somewhat works for us.
okay,
So it's, I
okay.
think, getting this kind of formalism for all the mesons, it's still open problem in QCD. So I asked Professor Nirmal also about this, and he also said the same thing, which is that I had the same doubt, which is that how approximate is approximate. So he said it works for this because of U and D quarks being small, but other quarks may not work. So that's the idea.
Okay. Mm.
But yeah, the idea is that this whole treatment of Goldstone bosons, Higgs mechanism, all this is fairly general and you can apply it to whatever system. This is another system where this applies. Okay, I think we are at 7:30. So we can now do the questions. Let's finish with solving the questions and then we can end the session. Okay.
Actually, I have a question. Uh,
Yes.
yeah, please don't do any homework questions because I haven't submitted them yet.
Yeah. No. These questions are always they are from they ask us not to solve assignment questions. So these are always different from the assignment questions.
Okay, that's
Yeah. These are last year's questions. So I think there are not many people in the meeting. So maybe I will just go through the questions and answers one by one because anyway we are low on time also.
okay.
So you guys can. I'll give you a minute or two to answer, but let's finish up. Okay, so this we just discussed, but the pion has a non-zero mass because leptons have a non-zero mass, all mesons have non-zero mass, light quarks have non-zero mass, making chiral symmetry not exact, gauge bosons have a non-zero mass. So, okay, maybe we have time, so you guys can try answering in the chat, whoever is there in the meeting. I'll give a minute in case someone wants to try answering, otherwise I'll go to the next question. Okay, so yeah, so the answer is C, correct, which is that light quarks, as we discussed just now in the last slide, light quarks have some small mass, so their chiral symmetry is not exactly not exactly there, so that's why they end up with a small mass in the theory. Okay, next question. How many massless Goldstone modes are formed when O5 symmetry breaks down to an O4? So again, I'll give like maybe little bit of time for people to answer. Okay, I'm just going to go to the answer because oh, yeah, okay. So the answer is D. So here, remember that the number of Goldstone modes that are formed correspond to the number of generators that are left, the difference in number of generators. Okay. So O5 is basically rotation in 5D space, if you can imagine that. And O4 corresponds to rotation matrices of 4 dimension. O5 is rotation matrices of 5 in 5 dimension because O3 is 3 dimensional rotations, right? The point is that you can calculate the number of generators. So I just found this. The basically SON, ON, all of them have a particular relation, which is that any group which is like O of n, orthogonal matrices of n, it has generate number of generators will be n into n minus 1 by 2. So for example, for SO3, which we are familiar with, it will be 3 into 2 by 2. So that's 3. And we know that there are 3 rotation matrices that are the generators of the SO3 group, right? Similarly, if it's SO4 or O4, this is going to be 4 into 3 by 2, which is 6. Whereas SO5 is 5 into 4 by 2, which is 10. So initially I had 10 generators, then I am left with 6 generators. So the difference of both of them is 4. And that's why the answer is 4. Okay, so right now in standard model, we don't have any SO5 or SO4 fields. But again, it's worth remembering that all these concepts are general. So, we can apply the Goldstone boson in this way as well. So there's a bit of explanation here of how to actually calculate the degrees, because generators is kind of like the degrees of freedom of the group. And you can find out how to find that. I've just given you the answer here. It's from a stack exchange question. Okay, basically you have 2n squared. If you have an n by n matrix, you have 2n squared times sorry, not 2n squared, n squared times entries, and then you have to impose what are the conditions that is given by the group definition. And when you remove those things, you get what is the number of generators. So the generators tells you the number of independent ways to construct the group, basically. Mm. Okay, all the standard model fields, that is the left-handed quarks, right-handed quarks, left-handed leptons, right-handed electron, Higgs boson, all of them coupled to which boson?
I don't know.
Okay, we'll go to the answer. So the answer is B. So remember that gluon is the color force. Color force does not act on the leptons, right? So it
Yeah.
definitely doesn't act on L and D. Pion is different. W1, W2, W3 are what comprise the weak force before the symmetry breaking. Remember, the weak force only acts on the left-handed parts. So it's only B, which is the hypercharge, which combines with, which is the U1 part of SU2 cross U1. Only B acts on all of them. All of them have some value of the hypercharge. Okay. So next question. In the absence of Higgs field, fermion masses vanish in the standard model because of what reason? Okay, I'll just go to the answers. So The answer is that as we discussed, the weak force is a chiral theory in the sense that it only acts on the left-handed particles. It has a very strict chirality, right? Okay,
Yes.
it has a very strict chirality in the sense it only acts on the left-handed particles. If we wrote a term that combined both left and right-handed particle, then the gauge invariance would be broken. That's why we cannot write any mass terms just like that. Only if there's a Higgs field, we can write some terms which are, combinations. So I think in the lecture notes there are once you write the Higgs field, there are the combinations of different fields that you can write. Some of them do have left and right combination, and that's how you can get it. Okay. So next question: in the absence of Higgs field, gauge boson masses vanish in the standard model because. Okay, I'll go to the answer. So the answer is that because of gauge invariance. So when you have gauge boson, as I said, is a consequence of the local symmetry of the theory. It's the force carrier, right? It won't act on the force does not act on the gauge carriers itself. So this whole chirality thing is not a problem. The weak force anyway doesn't act on the gauge boson. The point is that if we have a mass term initially itself, then that leads to gauge invariance. You can't in the beginning itself write a mass term in the Lagrangian. Only if the Higgs mechanism happens and the symmetry breaking happens, then only the gauge bosons get a mass. So that remember our example in the very beginning, I showed you about the difference between a global U1 and a local U1, right? So global
Yes.
U1 didn't have any gauge field and there was no mass also. Local U1 we had to add a gauge field, and initially we don't add any mass term, but anyway, because of the symmetry breaking, there arises a mass term in the Lagrange. So we can't first itself write it because then it won't be gauge invariant. Again, like it has to obey the symmetries of the theory. So whenever we write anything in the Lagrangian, it has to be consistent with the gauge invariances and symmetries of the theory. Okay. Chiral symmetry breaking is. Okay. So the answer is explicit and dynamical, the later implying it's also spontaneous. So explicit in the terms that you have explicit terms in the Lagrangian about it. Dynamical because, if I just write the theory and I don't have to specifically say that you have to do chiral symmetry breaking, right? You saw that just because the minimum is in this ring, or, there are not, it doesn't always have to be a ring, but because there's this degenerate vacuum solution, as a system cools down, or it chooses a minimum energy configuration, it's going to definitely break the symmetry. So that shows that it's spontaneous, it's not triggered by any outside influence. It's also not triggered by any particular force, right? It happens by the natural evolution of the system, because every system in the universe wants to minimize its energy. But in this case, when it minimizes its energy, it is forced to choose a state among many degenerate states. And this shows that it's a spontaneous, dynamical, and explicit uh, procedure. Okay. So Lagrangian is perfectly symmetrical, and yet the symmetry may break spontaneously. How come? So this we spoke about. What leads to, kind of the symmetry breaking in the first place? Or what leads to a particular state being chosen and symmetry breaking in the potential?
I would like to say initial conditions, but there is no time solution.
Yeah, yeah. So it is initial conditions. You're right. So yeah, the spontaneous symmetry breaking is because of the time evolution. It's also a factor in the sense of the dynamics of the system. But here, why the symmetry itself is breaking is because of initial conditions. So remember about the example of the pencil, which is that the pencil can fall anywhere in the circle, but because of some initial conditions of something that we are missing, it is choosing to fall in say 30-degree angle or 60-degree angle or something like that, right? So the initial condition is what decides where the symmetry will break. So you're right that the time evolution leads to the dynamical part of dynamic symmetry breaking, but the spontaneous symmetry breaking where the state ends up is because of the initial conditions. Okay, next question. So I didn't explicitly define Yukawa terms in my recap, but you came across this in your lecture. So what are the Yukawa terms?
Fermion masses.
So no, so Yukawa terms is something specific, which is the interaction between two fermions on a scalar. In other words, they are basically all these terms, right? One sec, let me just go back. So when we write the Higgs, we wrote these where we wrote these extra terms which are basically fermion, scalar, Higgs, fermion, etc. So these are the Yukawa terms. So they show up because the fermion field couples to the scalar Higgs. So these are the Dirac terms, Dirac kinetic terms. This is the covariant Higgs terms. These are the kinetic terms of the gauge theory. Then you're left with basically the Yukawa terms. So Yukawa terms are the name for these terms which couple the scalar Higgs field to the two different fermion fields. So the answer is 1 second. So answer is two fermions and a scalar. Basically left and right fermion and scalar. So again that kind of mimics the mass term, gives the mass term in the Dirac Lagrange. Okay, next question. Okay, so I'll go to the answer. So the answer is don't it's okay because the potential is always positive because the Mexican hat potential has an extra 5 power 4, or 5 dagger 5 to the square term. So that quartic term is positive. So it over compensates for this negative mass term. So the potential is always positive. This you can see in the diagrams of the Mexican hat I showed you. For example, here, okay, here it looks like that, but it's actually positive. So okay, so for example, here you can see that the potential is always positive. This is because it's in 3D. It looks like it's going down, but actually the potential it is bounded from below. So it doesn't. For example, in this you can see more explicitly. Basically, because you have this term, this compensates for this. The reason why this is called a negative mass term is because if you recall, always mass terms already come with negative sign. So in that sense, the definition of mass is like negative. It's just a convention. Point is that the combination of these two terms, because in potential, in Lagrangian, potential always comes as T minus V, right? So this is kind of like the negative of the potential. So in that sense, the mass term is negative. But again, it's okay because overall this term will always be positive. Okay, I think we are almost done. Okay, last question. Dark energy receives a contribution from Higgs potential because
A.
the answer is okay. So the answer is actually B. So I think I spoke about cosmology a few weeks ago. Basically energy, you saw that there are different energy content in the universe. Dark energy usually is what is believed to be accelerating the expansion of the universe, and it comes from the vacuum energy. Okay, so all the as the universe is expanding, the contributions from matter and radiation content is going down, because you can imagine that density is mass by volume. So if the universe is expanding, the volume is getting bigger, so the density goes down. Whereas dark energy is something which is uniform across space time. It doesn't depend on the volume. So that's why even though the universe keeps expanding, dark energy is able to actually accelerate the expansion of the universe. So whenever we have a dark energy in our system, it has to be uniform across space time. If you see, the Higgs is also like that. Higgs has that behavior where it dumps some energy into the universe, which doesn't decay with time. It doesn't depend on the scale of the universe, and that's why it can also contribute to the dark energy content of the universe. So this I spoke about week 3 or 4, whenever the cosmological constant problem was discussed. Spoke about this, so you can go check. I have given some introduction to cosmology. You can go and check in those lectures, and also in the actual lectures. Okay, that brings me to the end of the class. So today is a bit heavy because we had to go through a little bit of mathematics. These things are very confusing when you first learn them, and I had to relearn a lot of these things before this lecture as well, because these are not trivial, and also the mathematics is also, quite involved. But yeah, I would suggest that you sit and just, like, you can try writing down some of these things, then you can see for yourself, or you can try plotting the potential. That really helps you to crystallize these ideas. Again, for today's lecture, okay, I didn't put in my resources, but today's lecture I've used, let me just open last week's thing. So today's lecture, I've used QFT for the gifted amateur, and I've used symmetry and the standard model. I've used these two textbooks. Apart from that, in last week's lectures, I had linked for group theory, for QFT, for Lie algebra, some more lectures. You can go and check them out. Yeah, apart from that, this video is being recorded. The slides will be shared to you. I'll just share my website where I maintain all the links. This is my email ID. If you have something to discuss with me and I can discuss it in the next week's lecture, you can always mail me. Are there any other questions for today?
No.
Okay, if not, have a nice week, everyone. Thank you for joining. I'll see you next week at the same time. Okay, bye, everyone. Thanks.